NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve a two-tank draining problem using simple linear models, a clear time versus volume graph, and step-by-step algebra. Problem: we have tank A with initial volume 120 liters, draining at 3 liters per second. Tank B with initial volume 70 liters, draining at 2 liters per second. We will find which empties first and by how many seconds. Check if the volumes ever become equal while both contain water. And finally, find the time when the volume in tank B is half the volume in tank A. To build intuition, let us visualize both tanks. Tank A is larger at the start, tank B is smaller. Both drain steadily and linearly with time. Since the draining rate is constant, volume is initial volume minus rate times time. That gives V sub A of t equals 120 minus 3t, and V sub B of t equals 70 minus 2t. Let us place both models on a single graph of volume versus time. The horizontal axis is time in seconds, and the vertical axis is volume in liters. Empty time occurs when the volume hits 0. For tank A, set V sub A of t equal to 0. That yields 3t equals 120, so t equals 40 seconds. For tank B, set V sub B of t equal to 0. That yields 2t equals 70, so t equals 35 seconds. Tank B empties first, 5 seconds earlier. Next, check if the volumes are ever equal while both tanks have water. That gives 120 minus 3t equals 70 minus 2t, so t equals 50 seconds. But tank B emptied at 35 seconds, so at 50 seconds, B is already 0. Therefore, the volumes are never equal while both contain water. Finally, find the time when V sub B equals 1/2 of V sub A. Set 70 minus 2t equals 1/2 times parenthesis 120 minus 3t. That simplifies to 70 minus 2t equals 60 minus 3 halves t. Move terms to one side to get negative 1/2 t equals negative 10, so t equals 20 seconds. Summary: tank B empties first at 35 seconds. Tank A empties at 40 seconds, so the gap is 5 seconds. The volumes are never equal while both. Example work rate problem. 2 workers finish a job together in 18 days. If each worked alone, the first would finish exactly 15 days faster than the second. We will solve step by step for their individual times. Let's build an intuitive picture. We'll use 2 workers and a single whole job. Together they complete the job in 18 days. Step 1. Define variables. Let the first worker alone take x days. Then the second takes x plus 15 days. Step 2. Translate times into daily work rates. A time of x days means the rate is 1 over x jobs per day. Similarly, the second worker's rate is 1 over x plus 15. Together the combined rate is 1 over 18. Step 3. Write the equation for combined rate. 1 over x plus 1 over x plus 15 equals 1 over 18. Step 4. Combine the fractions over a common denominator and simplify. Step 5. Clear denominators by cross-multiplying. Step 6. Expand and move all terms to one side to create a quadratic equation. Step 7. Factor the quadratic. The factors are x minus 30 and x plus 9. So x equals 30 or x equals negative 9. We reject the negative time. Therefore, the first worker alone takes 30 days. Finally, compute the second worker's time. It is x plus 15, which is 45 days. Let's summarize everything with a quick visual. On this axis of days, mark 30 for the first worker and 45 for the second worker. Together, they need only 18 days since their rates add. Answer: first worker, 30 days. Second worker, 45 days. Mixtures and concentration. We start with 200 kilograms of a saltwater solution at 4% salt. We want to reach 7% salt. We will explore 3 paths: add salt, evaporate water, and a mixed scenario with limited salt on hand. Here is the starting beaker. For percent of 200 kilograms means 8 kilograms of salt and 192 kilograms of water. Case 1. Add x kilograms of pure salt. The salt becomes 8 plus x, and the total mass becomes 200 plus x. Set the concentration equal to 7% and solve for x. Case 2. Do not add salt. Let y kilograms of water evaporate. The salt stays at 8 kilograms, while the total mass becomes 200 minus y. Set the concentration to 7% and solve for y. Case 3. Suppose only 5 kilograms of salt are available. Add all 5 kilograms. Then the salt Suppose only 5 kilograms of salt are available. Add all 5 kilograms. Then the salt becomes 13 kilograms, and the total mass becomes 205 kilograms. Now evaporate water until the concentration is 7%. Solve for the evaporation amount, y. Summary. To reach 7% from 200 kilograms at 4%. Either add about 6.45 kilograms of salt or evaporate about 85.71 kilograms of water. If only 5 kilograms of salt are available and added first, then evaporate about 19.29 kilograms of water. The key idea is that concentration equals salt mass divided by total mass. Adding salt changes both the numerator and the denominator, while evaporation reduces only the denominator. Use that relationship to set up an equation and solve for the unknown change. In this lesson, we will find the average speed for a round trip when the going speed is 60 kilometers per hour and the return speed is 40 kilometers per hour. We will carefully visualize the motion, avoid a common mistake, and then compute the correct answer step by step. Let us picture two cities on a straight road. The distance between them is unknown, so we will call it x. First, the car travels from city A to city B at 60 kilometers per hour, and then comes back from city B to city A at 40 kilometers per hour. A common mistake is to take the simple arithmetic average of the two speeds. That gives 50 kilometers per hour, which is not correct because more time is spent at the lower speed. The correct definition is total distance divided by total time. The total distance is 2x because we go and return. The going time is x over 60, and the return time is x over 40. So the total time is x over 60 plus x over 40. Now substitute into the definition. Average speed is 2x divided by x over 60 plus x over 40. Factor out x and cancel it. We then have 2 divided by 1 over 60 plus 1 over 40. Adding the fractions gives 5 over 120, so the result is 2 divided by 5 over 120, which equals 48 kilometers per hour. Intuitively, notice that the car spends a longer time at the slower speed of 40, so the overall average must be less than 50. Watching the car, the return trip takes longer than the outbound trip. This matches our final answer of 48 kilometers per hour. Therefore, the average speed for the round trip is 48 kilometers per hour. Example age problem. A father is 32 years old, and his son is 5 years old. After how many years will the father's age be 10 times the son's age? We'll build an intuitive diagram, set up an equation, solve it step by step, and then interpret the answer. Let's first visualize time on a timeline. 0 is now. Positive is in the future to the right. Negative is in the past to the left. We'll also place our father and son at the present with their ages. Define the unknown. Let t be the number of years from now. After t years, the father's age will be 32 plus t, and the son's age will be 5 plus t. The condition says father's age equals 10 times son's age. That's our equation. Now solve step by step. Distribute the 10. Move like terms to opposite sides. Then divide. A negative t means we must go to the past. T equals -2 tells us 2 years ago this condition was true. Let's mark t equals -2 and verify the ages. 2 years ago, father was 30, son was 3, and indeed 30 equals 10 times 3. Conclusion: there is no future time when the father will be 10 times the son's age. It happened 2 years ago at t equals -2. In this lesson, we will discover all pairs of 2-digit numbers whose product remains the same after swapping the digits across the two numbers. The classic example is 46 times 96 equals 64 times 69. We will follow a clean algebraic recipe to find every such pair. Here is the motivating example. Notice the digits 4 and 6 and 6 and 9 are swapped across the two numbers. Yet the product is unchanged. Step 1. Represent the first number as 10x plus y and the second number as 10z plus t. Here x and y are the tens and ones digits of the first number, and z and t are the tens and ones digits of the second number. All digits are between 1 and 9 because we consider valid two-digit numbers. Step 2. Translate the statement product is unchanged after swapping the digits across. Swapping means the new pair is 10y plus x and 10t plus z. Therefore, the equality of products is left parenthesis 10x plus y right parenthesis times left parenthesis 10z plus t right parenthesis equals left parenthesis 10y plus x right parenthesis times left parenthesis 10t plus z right parenthesis. Step 3. Expand both sides. Collect like terms. On the left, we get 100xz plus 10xt plus 10yz plus yt. On the right, we get 100yt plus 10yz plus 10xt plus xz. Step 4. Set the expansions equal, then subtract matching terms on both sides. The 10xt and the 10yz cancel out. We are left with 100xz plus yt equals 100yt plus xz. Move terms to one side to get 99xz equals 99yt. Divide by 99. The key relation is x times z equals y times t. Step 5. Because x, y, z, and t are digits between 1 and 9, we enumerate factorizations that make x times z equal to y times t. Here is a compact list that will generate all the valid pairs we need. Step 6. From each product equality, we build two-digit numbers. The first pair is 10x plus y and 10z plus t. The swapped pair is 10y plus x and 10t plus z. Each equality shown here yields concrete examples like 12 times 42 equals 21 times 24, and 13 times 62 equals 31 times 26. Finally, collecting all outcomes from our enumeration gives the full list below. These are precisely the two-digit pairs whose product stays the same after the cross-digit swap. The heart of the method is the compact relation x times z equals y times t. It converts a word pattern into a clean number theory search over digits. Great work following the complete derivation and the enumeration of all solutions. In this lesson, we will solve a two-digit number puzzle step by step using a clear algebraic model and see why it actually has no solution. Let the two-digit number have tens digit y and ones digit x. The tens digit is 4 less than the ones digit, so x equals y minus 4. And the number with reversed digits is 27 more than the original. We will build a small place value diagram to visualize this. From the statement, the tens digit is 4 less than the ones digit. That gives us x equals y minus 4. Also, reversed minus original equals 27. The reverse number is 10x plus y, and the original is 10y plus x, so the difference is 10x plus y minus 10y plus x equals 27. Now substitute x equals y minus 4 into the difference equation. We get open parenthesis 10 times y minus 4 plus y close minus 4 plus y close parenthesis minus open parenthesis 10 y plus y minus 4 close parenthesis equals 27. We simplify both sides carefully, distribute the minus sign, and combine like terms. We obtain 11y minus 40 minus 11y plus 4 equals 27. The 11y terms cancel, leaving negative 36 equals 27. This is a contradiction. A false statement means our system of equations has no solution. There is no two-digit number whose tens digit is 4 less than the ones digit, and whose reversed number exceeds the original by 27. For intuition, look back at the... In this lesson, we solve a classic two-digit number puzzle using algebra and a clear diagram. We are told two things. First, the tens digit is 3 less than the units digit. Second, the number with digits reversed is 27 larger than the original number. Let's visualize a two-digit number. The number has tens digit x and units digit y. Reversing the digits makes tens digit y and units digit x. Algebraically, the original equals 10x plus y, and the reversed equals 10y plus x. Now write the two conditions as equations. From condition 1, x equals y minus 3, so y equals x plus 3. From condition 2, reversed minus original equals 27. Open parenthesis 10, y plus x close parenthesis, minus, open parenthesis 10, x plus y close parenthesis, equals 27. Substitute y equals x plus 3 into the difference equation. That gives absolute value brackets 10 times open x plus 3 close plus x, minus 10x plus open x plus 3 close, equals 27. Expand and combine like terms. We get open parenthesis 11x plus 30 close parenthesis minus open parenthesis 11x plus 3 close parenthesis equals 27. Subtracting cancels the 11x terms and leaves 30 minus 3 equals 27, which is a true identity. 27 equals 27. An identity means the two equations are not independent. They both say the same thing, y minus x equals 3. So any digits with y equal to x plus 3 satisfy the algebra. But digits must be between 0 and 9, and the tens digit cannot be 0. Therefore, x can be 1 through 6, and y equals x plus 3 gives the valid numbers. Here are all two-digit solutions: 14, 25, 36, 47, 58, and 69. Each satisfies that the reversed number is 27 more than the original. Conclusion: the puzzle has infinitely many algebraic solutions along y equals x plus 3. Restricting to valid digits gives exactly 6 two-digit numbers: 14, 25, 36, 47, 58, and 69. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.